This is the inaugural edition of the Race Summit Connect. We're really glad that you decided to join us today. Let me go to the next slide so it doesn't look like we're starting in a few minutes. There we go. We're going to begin today with a look at the current state of machine learning, artificial intelligence, distributed computing, and the future for these things. Our guests today are two industry leaders who've been leading the charge in both spaces, Michael Jordan and Jan Stojka, who I'll introduce shortly. My name is Dean Wampler from Anyscale, and I'll be your host today. After the talks, we'll have our two speakers join me for Q&A and a panel discussion. We encourage you to add questions to the Q&A feature in the dialogue, which I'll show you in just a moment. But first, I want to give a couple of thanks to our community partners who helped us organize this event today by spreading the word. The RISE Lab at the University of California at Berkeley, various meetup groups around the country, around the world even, and some various tech slacks that some of us belong to, in particular in Chicago. I'd also like to tell you a little bit about some future events we have coming up that you might want to check out. We're rolling out new tutorial materials under the umbrella of Anyscale Academy starting May 27th. This will actually be a live event, although the materials will be available for on-demand use. So you can sign up for that if you want to join the live event on the 27th. And our next Race Summit Connect event will be on June 10th. The road to AutoML, the challenges of hyperparameter tuning will be the particular focus in the broad space of AutoML. You can find out more about all of these events and other events that are coming in subsequent months at anyscale.com/events. About today's event, we do ask you to ask questions through the Q&A feature that you see at the bottom of your Zoom UI. That'll be the best way to interact with the speakers. I'll be reading the questions for the video and get their feedback. Since this is our first event, we'd love to get your feedback, suggestions, and so forth. You can email us at this address. And finally, we'd invite you to tweet quotes or whatever you want to say about the event. You can either use the hashtag Race Summit Connect or one of our Twitter accounts, Anyscale Compute or Ray Distributed. And yes, we will post the slides and videos. We'll probably do that later this week once we've gone through and edited the videos and so forth. We'll post a blog post to anyscale.com so you can find out more about it. Okay, and actually the videos will get posted to the Anyscale YouTube account, and we'll have the links to the slides in the blog. All right, it's my pleasure now to introduce our first speaker today. Michael Jordan is Pihong Chen Distinguished Professor at the Department of Electrical Engineering and Computer Science, the Department of Statistics at the University of California, Berkeley, and he's also a co-founder of Anyscale. His topic today is the decision-making side of machine learning, computational, inferential, and economic perspectives. Welcome, Michael.
Thank you. So it's my pleasure to be here. I'm very pleased to be joining and sharing the stage with my colleague Jan Stojka from RISE Lab. Ray and Anyscale are very much the fruits of collaboration between machine learning researchers and distributed system researchers. So I want to give you the machine learning perspective today on where things are heading and what kind of workloads you might think about in the future. I think there's a tendency to think that all the workloads are going to be just more data and more TensorFlow. There's certainly some truth to that, but there's a whole range of other problems that are going to be emerging that systems people need to start to think about. All right, so let me bring up my slides. Take a second to do that. So I'll be focusing on the decision-making side of machine learning. What do I mean by that? Well, I like to think of machine learning as having two sides to it. There's the pattern recognition side, which has really been the focus of much of the work and much of the discussion in the last several years. So platforms like TensorFlow and PyTorch have turned this into a commodity. Pattern recognition roughly means large data sets, labeled data sets typically, and gradient-based methods that find patterns in those data sets that can be used to predict future labels or to try to find structures inside the data. You don't have much mention of decision-making in that picture, and in fact, the current generation of pattern recognition research has very little focus on decision-making. I think that the emerging future will have a lot more focus on decision-making, individual high stakes decisions. And what I mean by high stakes are consequential ones. It's not whether there's a rabbit in the image or not, but it's rather, should you have a certain medical operation, or should you build a factory in some part of the world, or so on. Explanations for decisions and dialogue about decisions. This isn't just explaining a neural net. It's explaining the rationale for a decision and what else could have been decided. The kind of dialogue you might have with a doctor if you're making an actual consequential decision. It's about sequences of decisions, and I don't just mean reinforcement learning. I mean large-scale decisions over time made with kind of an endpoint in mind. Multiple simultaneous decisions, where it's not just even one person making decisions, it's large numbers of coupled people making decisions. In fact, when you start talking about multiple decision makers, you have to start talking about market mechanisms. So I hope you see the scope of this is really, quite astonishingly big. In an era like COVID, you can start to see all of this kind of emerging, that there is a worldwide thing happening right now that involves not just a virus on one side, but on the other side, there's computers, and there's decisions, and there's data, and there's people, and there's a whole array of technology meets the real world. And we have to think about what that technology is and how it's overall making decisions which are good ones, very non-trivial. So let me just dig into this a little bit more. You might be excused to think about decisions as just a threshold on a neural net, right? What could be better than that? So imagine that you go to the doctor's office, and the doctor measures things about your body and measures your genome and maybe forms a 50,000 dimensional feature vector and puts that into the world's best neural net that's been trained on all the world's medical data, whatever that might mean, okay? And the output of that neural network is supposed to predict whether you're gonna have a disease or not. And so suppose that some output is over 0.7, and over 0.7 means that it's likely you're gonna have a heart attack. Is that actually a meaningful decision? Well, no, you're not going to just take that, nor would you take a doctor's assertion you're about to have a heart attack at face value. You would first of all ask, what's your uncertainty? What are your error bars there? We don't tend to talk about error bars a lot with neural nets. We assume we have so much data that there aren't error bars. Well, that's not true in the real world. There always are error bars. You want to ask where those error bars come from. Is it because the data was different than it's not relevant for me, or is it data that was gathered years ago, or data on different machines, and so on and so forth. So you want to start a whole dialogue. You also want to talk about provenance. So where did the data come from as part of that dialogue? You want to be able to ask about counterfactuals. What if I were to do something different? What if I were to eat more fish? What if I were to exercise more? Would that change your view? And things like, oh, I remember now that I had bronchitis when I was a kid, and that might affect my lungs, and the doctor should take that into account. That was probably not data that was in that big neural net. In fact, the big neural net is not going to have much of the data that's relevant to these kind of decisions. You will remember it in the moment, or it was just forgotten in some way. It didn't feel it was relevant. So dialogues involve all this kind of resampling of other possible data sets and trying things out. All right, so that's kind of just even one decision with one that has consequences. There are also, sets of decisions across a network. It's going to be not just one person's medical decision, it's how those relate to other people's medical decisions. And that's going to happen across large numbers of people. That's going to happen over time. There are going to be asynchronous decisions. There'll be streaming and so on and so forth. And then finally, even broader, we're going to have to think about decisions where there's scarcity and competition. Current machine learning has not thought this way. It's been about one data set or maybe several data sets inside of one computer for making one decision or a sequence of decisions. That's not the real world. In the real world, there's scarcity and there's competition. Again, think about COVID. We have scarcity of all kinds of resources, and they have to be allocated in various ways. So one person's decision interacts with other people's decisions. But not just COVID. Think about transportation. We can't send everybody down the same street. And we can't be the ones deciding. Somehow they have to independently make up their minds. So there has got to be some notion of competition. All right. So in fact, if you think about decisions this way, first of all, it sounds more realistic. We're now talking about the half of machine learning which has been neglected in its real world. But also we got to talk about distributed computing in this context. What does this mean now, distributed computing in the decision-making context when we have planetary scale decisions? Isn't there a problem emerging, which is we're coupling all these decisions, that everything's going to get tangled up again? And that's just not the right way to think. So microeconomics is the field that studies market design and market analysis. And markets are a mechanism whereby things get decoupled. Okay, even though we're all part of an economy and we go into a market and we're in principle all coupled to each other, there are mechanisms that are studied in economics, but were developed before economics even existed, that allow things to be decoupled. So in fact, prices are exactly that kind of notion. They're a number which decouples decisions. I don't have to know everything about you or all the facts that led you to think a certain way. All I know is that you accept a certain price point. And that price point will be argued about, part of an auction or whatever, so that what you give is an honest reflection of what you actually know. And that's all I need for me to make my own decision. So notions like prices are precisely a way of decoupling. Also, there's other ways of finding equilibrium in markets, matching algorithms and so on, which do this in local ways. All right, so when we start to turn machine learning towards markets and think about blends of microeconomics and machine learning, the systems consequences of that are not necessarily things where you get tangled up. In fact, it can be quite the opposite, that things will be more contextually relevant and less tangled up. But we have to design new algorithms that think this way, and we have to design new platforms that allow us to operate in this way. Okay, so this is not entirely new concept. Markets can be thought of as algorithms. That's an idea that others have talked about. They bring in goods into a city in every day in and out. They are based on localized decisions by agents which are not having to use most of their brain to make the decision. They're adaptive, they're robust, they're scalable, and so on and so forth. What I'm really advocating is that that perspective is correct, and that what was missing, however, was machine learning. It was missing the use of data to define the preferences and to define the way that these multi-way markets will work, how they connect up to each other and work at scale and work for long tails. Now, of course, markets are not a panacea. They're not perfect. They have all kinds of issues and problems. But that's good. That means there's all kinds of new research opportunities arising if you think this way about data analysis and decision making and markets altogether. There's going to be amazing new opportunities. So on the academic side, I'm going to talk just briefly about one example, and then I'll be done, of a project I've been working on. But just to give you a list of some of the others I've been thinking about and starting to work on, multi-way markets where you learn your preferences, multi-way markets in which you have recommendation size systems on both sides of the market, so that you're not looking at all possible items or goods or people. You're looking at a subset given by your past history. Information asymmetries, latent variables, and data collection in strategic settings, and so on and so forth. So all kinds of interesting problems where machine learning meets up with economics. I also have another talk I give, which is less about the academic side, and it's more about the business model side. How do you build healthy markets for things like music has been a focus of mine. How can you make a company that actually brings together producers and consumers on both sides and creates a new market for things like music that doesn't just flow data from one side to the other, but flows economic value from one side to the other. So I think that's an emerging business model that is going to use these academic ideas, but it's its own story. All right, so just one example of a project that allows you to start to think this way. It's kind of a thought experiment in some ways, but leads to a real algorithm. So it's with my students Lydia Yu and Horia Mani at Berkeley, competing bandits in matching markets. So multi-armed bandits are my favorite machine learning problem, much more preferred to me than supervised learning, which is more of a memorization problem from my point of view and less of a learning problem. A multi-armed bandit is a learning problem. I have several options and I don't know which is the correct one. So I try them out a little bit and I start to orient towards the one which is working the best. So I get a reward from each of the choices. And after I get some rewards, I start to learn about the reward distributions and I start to balance exploration and exploitation. Okay. So hyperparameter tuning is certainly an example of this, but now we're back in the pattern recognition world. I want to be more on the decision making world. Okay, so there's a famous algorithm that solves this problem. Sort of two algorithms. Thompson sampling is one. The other is upper confidence bounds, frequentist and Bayesian. Upper confidence bounds don't just keep the mean reward you've received so far, but they keep an error bar. And they take the upper range of that error bar and you pick the arm that has the highest upper range of the error bar. So briefly, what that allows you to do is pick arms that look pretty good, but also explore arms that have not been explored very much. They have a high error bar. So we would update our error bars here after we pick these arms a little bit. All right, so there's a vast literature on this. These algorithms like upper confidence bound have nice properties. They have a low regret, meaning that you'll do just about as well as that if you'd known the answer a priori. Over time, you'll learn, and large literature on this. Okay, so we're going to put that together with matching markets. I hope you all know what a matching market is. On one side, you have buyers, and the other side, you have sellers, and each side has a preference over the other side, and we want to match things up. So there's the Gale-Shapley algorithm, which is a famous algorithm that does this, kind of a very simple polynomial time algorithm. And this is widely used for things like kidney exchanges and interns in hospitals and so on and so forth. Now the issue here is that you have to assume you know the preferences a priori. Okay, in real life markets, many times the buyers and sellers don't know the preferences, and in fact there might be millions of items on each side. So there's no way you're going to be able to assay all their preferences. How do we deal with that? Well, we're going to argue that we want to bring bandits together with matching markets. Okay, so we're going to learn our preferences by experience, and that then will feed into the matching. So now imagine you have competing agents, and they both can pick the arm simultaneously. If both of them happen to pick a single arm, only one of them is going to get it. The other one gets a 0 reward. Okay, who gets it? Well, the other side of the market has preferences back on the left side of the market. We don't know those preferences, and those would again be learned as part of the overall game. All right. So we have a bandit market. Agents get noisy rewards, and if there's a conflict, only one of them gets the reward. All right. So there's a notion of regret here, which is the best set of rewards you could get relative to what the Gale-Shapley algorithm would give you if you knew the rewards a priori. Okay, that's a notion of regret. We define an algorithm, which is what we call GS-UCB. It is a blend of Gale-Shapley and upper confidence bounds. Roughly speaking, you form the upper confidence bounds on all the arms. Each agent does that. They give those bounds to the Gale-Shapley algorithm, and it runs a matching. Okay, so that's roughly the idea. And we're able to prove a regret bound for this. Just briefly, it is logarithmic in the number of rounds. That's very favorable. That shows you really are learning. If this were growing linear, you're not learning. If it's growing sublinear, you're learning. And there is a term in the denominator there, which reflects the presence of other agents. If I'm picking an arm and Jan Stoika is picking the arm, and I start to see that Jan is always winning when we both pick the same arm, I'm going to have to explore more than I otherwise would. I'm going to look at the other arms as possibilities. I know I might be losing my favorite arm. And so that I will pay a penalty and regret there, and it's reflected by that delta squared. So that's the Stoika term in the equation. All right, so that's the picture. Let me just finish here, but just say a couple more words about UCB can be used in all kinds of other contexts. This is an error bar algorithm, and surprisingly, it hasn't been brought into many other contexts in current machine learning. So if you bring it into context of reinforcement learning, which I've done with my 3 colleagues here, here's just a very brief picture of reinforcement learning to remind you. You could argue about model-free and model-based machine learning. In one case, you form reinforcement learning, a model. The other case, you don't. Here is Q-learning, but where we add a bonus, that BT term, which is a UCB term. And in that case, here's my last slide. At the bottom there in gray, you'll see the analysis of Q-learning with UCB, and you'll see a regret, which is square root of the number of rounds, T. Just above that, you'll see things like T to the 4th, 5th power and all. That was viewed as the penalty you had to pay to be model-free. We're seeing relative to the model-based algorithms up above, which are all square root of T, that the new analysis with UCB is also square root of 2. So you do not lose by going to a model-free paradigm here if you appropriately use something like UCB. Okay, so I'm done with the talk. That was a quick little dash into one particular problem, but I want to return to my big picture here, which is that machine learning is not just pattern recognition and large data sets and TensorFlow and PyTorch. That's certainly part of the picture going forward, but a lot of that is just kind of dumb search and dumb labeled data and so on. So we want to think about now decision making. And so the agenda becomes distributed pattern recognition and distributed decision making. All right, so we need to think about the platform, and we need to think about the machine learning problems. And let me just say that Ray was conceived with this already in mind several years ago. thinking about distributed reinforcement learning, thinking about distributed decision making. So I'll now turn it over to Jan, who will give a story about distributed platforms. Thank you.
Okay, thank you very much, Mike. Jan, before we go to you, there's a couple of questions I'd like to ask while we're fresh that the audience posed, if I may, Mike.
All right.
The first one is someone asked about aspects of planning in this picture. So you often don't think of markets as being about planning, but yet economics also has that aspect of planning for the future, anticipating the future. And I wonder if you've thought about how that would fit into this picture.
Fantastic question. I think of planning as very much part of decision making. And I think of planning as a success of AI that's not that heralded. Planning really is often market-based. That's what a good economic system does, is it makes plans. It just doesn't have a decentralized plan. It's a decentralized planning mechanism. And the side of AI that did planning just didn't do a lot of machine learning. Okay, it was very far away from machine learning. And so part of the story here, I didn't say the word planning, I probably should have, is to bring the planning style into contact more with machine learning. It just, for me, that often has a heavy feel to it, that you're bringing centralized planning algorithms into contact, and I don't want that. I want these lightweight, more economic style things, but I think of them as doing planning. So that's a great question. In fact, ML and AI, what is the difference right now? I mean, historically, there was a big difference. Right now, most of AI is just ML, but that's not true because AI has a planning success story inside of it. So, AI is kind of ML plus planning right now, and I think more of that would be better. Great question.
Okay, maybe two more quickly, and then we'll switch over to Jan. What about the fact that the decision space can be extremely complex, even infinitely large? Is there ways that we can prune that down? Have you considered that problem?
Yeah, so recommendation systems are one part of this. It sounds easy and simple, but to build industry-style recommendation systems like Amazon did and all is really challenging. Okay, you need to build recommendation systems on the decision side. If I go into a city that I don't know and I think about the 10,000 restaurants I might go to, that's a large space, right? I can't explore all that space. I can't even think about it. But hopefully millions of other people who are somewhat like me have been in that city, and the data that they've accrued flows over to me in a good recommendation system that's decision oriented, and will help me it will help hone the market down to maybe a few dozen restaurants which are most appropriate, and then maybe I'll get bids from those restaurants, and we'll have a whole market mechanism in a smaller space. So that's just one quick answer, but there's lots more answers to that. Yes, thinking about millions and hundreds of millions of items on the decision side is well within scope of our research, and it's very much the problem we should be thinking about it. It's partly pruning, and it's partly low rank structures and market mechanisms, again, to kind of focus.
The last question will ask for now. There have been attempts to restructure microeconomics on the foundation of game theory. And I wonder if you think there's important aspects that should be applied in this case as well.
Every time I said the word microeconomics, you can substitute game theory if you want. I think of microeconomics as basically built on game theory. It's kind of the calculus of microeconomics, whether it's cooperative or competitive. You just sort of bring in a little classical market ideas like supply and demand curves and all that, and you add, the game theory formalism to it. Mathematically, it becomes a lot of saddle point problems and a lot of dynamics in certain spaces, and that doesn't look that distant from machine learning gradient descent kind of ideas. So, if you're a mathematical kind of person, Hamilton-Jacobi-Bellman equations are very much a link between all of these things. And so I think that there's going to be a lot of flow at the mathematical level, and in addition to the flow at the conceptual level that I've been talking about here.